Hello students, so today we are going to study about relations and functions. Okay, I would request you to recall all those concepts which you have learned in class 11th, which are of course related to functions and relations and functions. So some of them could be like what is the definition of a relation, or what is the definition of function, and how many types of functions you have learned, like polynomial function, modulus function, sinum function, and your fractional function, and there are some other types of functions. Okay, so you must look after them. And what is the meaning of a particular function, you have to understand. You can go back and just have a look on all those concepts, and if you have any doubt on those things, then you can ask. And of course, you must have learned Cartesian product. Okay, Cartesian product of two sets, and in earlier class we have discussed about your sets. Okay, what is a set and all. So from here we will start with functions and relations and functions. What must have like inspired our mathematicians to look all to look after this concept. Okay, so see why I'm emphasizing on thinking about why we should learn it, and what would be the necessity which our mathematicians have encountered, and then they felt the need, okay, let's understand this topic and this thing and then build upon it. So thinking about such things, thinking in this way, you will of course get a clarity why I'm studying this particular topic or particular subject. Then you will feel an importance of learning this concept, right? And another reason to talk about the thing that what is the historical perspective and what should we learn, what inspiration for our mathematicians behind these things, that when you encounter some similar situations in your career or in your life, in your course, so you will also have a mindset which will force you, which will inspire you to think differently. Okay, can we build a system, can we theorize something, conceptualize something that can help us to come out of the current problems we are facing, or which we are not able to solve with the existing system. So knowing these things is important because of these things, right, which will keep the fire inside you burning. Okay, of course there are some mathematicians, Leibniz and your Dirichlet, who worked on the relations and function deeply. They were the pioneers. Okay, its conceptualization was done by Dirichlet, Leibniz, Newton people, those mathematicians. When we know a function, we must be aware of F equal to ma, right? In physics or somewhere else. What is it? It is force, and it is equal to acceleration multiplied by its mass. Okay, by of a body. So this much of force will be applied. So we can say mass is fixed. Okay, acceleration going to change. We can say F is a function of force is a function of A equal to ma. Means force is a function of acceleration, right? So which depends on acceleration. If acceleration is more, the force exerted upon the object will be more. And help mathematician to define, to describe many things, many geometrical shapes which they earlier could not play around that. They of course face some difficulty to describe how a curve is. Okay, these equations are helping us to describe these geometrical shapes and helping us physics also, and in many other fields. That's why it is very important to understand what a function is, what a relation is, what is the difference between a function and relation. So in class 11 you must have understood what is the definition of a relation, right? So relation between two non-empty sets A and B is a subset. Subset we have learned it. So in our set theory class. So it is a subset of A cross B. A cross B is Cartesian product of A and B. So let's say if I define you some briefly what is a Cartesian product of A and B. Let's say A is a set something A, B, and B is a set your C, D. Okay, so A is a set, B is a set. These are both non-empty. Non-empty means these sets have some elements, okay, in them. So A cross B will be product of A comma B. It is like pair A C A D and B C B D. Right? It's a simple product. Means A was paired, A is paired with C and A is paired with D, and similarly B is paired with C and B is paired with D. Okay, so this is a Cartesian product of A two sets A and B. So relation from set A to B is a subset of this Cartesian product. Okay, so yes, now let's go. If I write it mathematically, how would I write it? So it's like R is a subset of, okay, and so like we denote it like from A to B. Okay, so it's we write it like this way: call your domain, and this will be called your codomain. Okay, it's a codomain. And now, so let's understand relation by an example. Okay, so this is a concept. These are two non-empty sets A and B, okay, and there is a relation. Now we have to show that how many elements of A with these relations are related to B, okay. So if you see, this is a relation y equal to 2x, where x is from A and y from B, okay. So now we have to check for who are those elements in A who are related to B. So when we place 1 or substitute 1 for x, so we get 2, but 2 is not in B. And if you substitute 2, we get 4. 4 is in this. So for this one will be, these two elements are related. These two elements means 2 of A is related to 4 of B through this relation. Okay, and 4 of A, similarly 4 of A is related to 8 of B through this relation. So we can say this is a subset. Okay, this is a subset of course we can see it clearly that it's a subset of if I actually subset of A cross B, right? So we can see that A cross like R is a subset of A cross B, right? So one main thing to understand here is we cannot expect that every element of A will be related to every other element of B. Okay, it's not real necessary. Okay, so this is a simple thing to understand. And if you go in common language, relation is relating with someone. Okay, so it's one person is relating to multiple person. Let's say A is relating to A1, A2, A3. Okay, and many other could be. Okay, so one person can have multiple images, means to whom they are relating, whom A is relating are the images of A, right? So these will form range of for the relation. Let's say if I ask these as a relation, cousin, means A have these many cousins. Okay, so what type of relation is this? Cousin one relationship, right? We can say. So it, with this relation, A has how many elements are in range of this relation? 3, A1, A2 and A3. Okay, and how many elements are in domain? Only 1, right? So this is what if I write it in a relation sense, how would this be? So it will be like A1, A2, A3. Okay, so this will be the relation or subset. Okay, yeah. So now we will understand types of relations. Okay, so let me first jot them down one by one, and then we will discuss them at once. Okay. What is an empty relation? Empty relation is a of course set A and there is set B, and if I am saying R is a relation from A to B and it is empty, what it means? There is no element of A which is relating to any element of B, so it will be empty. So in that case I will say, let's say with an example. Okay, so yeah, this is an example of empty relations, and here A is a set of 1, 2, 3, B is a set of 7, 9, 11. Okay, and relation we have defined here is as x, y, comma, means it is written in your set builder form. So relation is it x comma y such that y is equal to 4 of x, means 4 multiplied by x, where x belongs to A, y belongs to B. Now if we put or substitute values from A and we make a roster form, or yeah, we get a set that there is no element of A which is relating to any element of B through this relation. So in that case this relation will have no element in it. Okay, they say it is empty, and yet it is subset of what? It is a subset of A cross B. Means this relation is still a subset of A cross B. So this is an example of an empty relation. Okay. Now comes universal relation. Universal relation is between two sets, two non-empty sets, is the Cartesian product itself. When, means how, let's understand. Okay. So universal relation will be from P to Q is when, means when we say that this is a universal relation when R is equal to P cross Q, means when the relation itself becomes the Cartesian product of the two sets, two non-empty set, then it is called universal relation. Means every element of P is related to every element of Q, right? So in this case we can say it's a universal relation. So can you find an example of a universal relationship? So yeah, of course they can be. Let's say it's a so see, here P is a class 12th students. Okay, P is a set of class 12th students, and same I'm taking Q also as a P, means like class 12th student, both are same sets. Okay, so in this case what will happen and how we define, I have defined relation here. Every student of P is a classmate of every student of Q. Okay, so in this case what will happen means every element of P is relating to every element of, okay, each and every student of P or element of P is relating to every element of Q. And what will happen then means there will be how many elements in R? There will be P times Q, means like if I say there are n elements in P, and just a minute, so number of elements in P times number of elements in Q, right? So and what will be this? It will be the exactly the number of elements in a Cartesian product of P and Q. So it will be how much? N times of, so this will exactly be equal to n times of, means like number of elements in the Cartesian product of P and Q. Okay, so in this way we can say this is a universal relation. When we will get a universal relation? When each and every element of P or the domain is related with every element of Q, or codomain we can say. So in that sense, in that case we can say domain and range will be same. Okay, for universal relations domain and range are same, right? Yeah, this is what, right? Now comes equivalence relation. What is an equivalence relation? Actually equivalence relation is a special class of relation, right? Yeah, so let's understand about it. So equivalence relations is a special class of relation when we call a relation to be equivalence when it is, if it is from a non-empty set to itself. Okay, so here we can say that the both domain and codomain are same. Okay, so we will call R as an equivalence relation when it is, if it is reflexive, symmetric and transitive together. Okay, so it has to follow these three criteria to be called equivalence relation. When we call a relation as reflexive, when for each element of this domain each element is itself belong to or related to it some way. Okay, so A comma A is belongs to this relation. This is a set. Okay, it is a set or subset of, you can say yeah, it's a cross A cross A, right? So yeah, for it will be true also for these. Okay, so each element of A is also related with itself. Okay, it must be related to itself. So that's why we are saying A comma A belongs to R. And when we call it symmetric, if A and B are related with each other through this relation, then B comma A also be related with this relation. Okay, must also be related with this relation. Okay, and when we say a relation to be transitive, when if for each ABC three elements, for every three elements in A, in the set A or domain A, if A and B are related with each other and B and C are related with each other with the same relation, then A and C must also be related with each other with the same relation. So these are the three properties or criteria or sub-relation criteria which makes together, if fulfilled together, imply that this relation from A to A is an equivalence relation. Okay, So this is what these three types of relations we have like talked. Okay, so let's move on. So before moving to functions, I would like to introduce to you an important concept that is called equivalence class. It is related to equivalence relation. So equivalence class is more related or is the next step which we get from equivalence relations. Okay, so if a set there is a equivalence relation from A to A, and element of A are related with how many elements? Let's say A1, A2, A3 and on. Okay, A1, A2, A3 and so on. And element B through relation R is related to B, B1, B2, B3, Bn and so on. Okay, so in this case we say this is a class. Okay, this is a class of A. Okay, this is an equivalence class of element A which contains elements which are related to through this equivalence relations with A. Okay, similarly class B is called, or is the set consists of all those elements which are related with B through this relation. So we can say that this set can be written as, or can be expressed as the union of these classes. Why? Because these classes contains elements, and it is worth mentioning that means no element of A, class A, will be in class B, and same thing, no element of class B will be in class A. Okay, so this is disjoint property of equivalence classes. So in this way, if you, let's say I give it a name A1 class, A2 class and so on, and there are some other classes, let's say AK classes, okay, which yeah, we just assuming it. Okay, so in this way we can write A as the union. Okay, it will be, so we can write it A1 union A2 union. Yeah, so this is a this expression says that A is a disjoint union of all the equivalence classes of its elements. Okay, so yeah, so in this way we can express a set in its as a union of its disjoint equivalence classes. Okay, and where AI does not equal to AJ for I does not equal to J, means if two equivalence classes can't be same. Okay, if any of them, you will learn this property in future, that if any of the elements in two equivalent classes are same or common, then two equivalence classes are either same or either that thing is not right. Okay, so this is a small thing which you will of course learn in your later classes in your higher education. But now we come at functions. So it's of course a kind of relation, but there's a minor difference. So if I say f is a function from a non-empty or a function from a non-empty set from A to a non-empty set B is a subset of Cartesian product of A cross B, where each element of domain A is uniquely connected or related to the element of B. Okay, so there is a one important condition actually came, which is different from our relation, where in relation it's just a subset. Relation is a subset of Cartesian product of A and B, right? But in case of function, each element of domain A is has unique image in the codomain B. Okay, so this uniqueness makes a function different from a relation. Okay, so I'll explain you with an example. So let's. So these are two sets. It's a codomain, it's a domain, and it's your codomain. Okay, and we are defining a function from here to here, or let's relation. Okay, somewhere. Firstly, I'll just explain things. Okay, so let's say this one. So this is some connection between two sets. Okay, and now we can see it. You tell me, is it a function or a relation? What do you think? So it is actually a relation. Why? Because element of this domain A and B, this A element is connected with two elements, has two images in codomain Q. So you can see this one, and same thing goes for D. D has two images. But in case of your function, we have only one image. One image, I mean, means it will give only one value. If I give some input, it will give me only one value, unique value. But in case of function, I can relate with multiple, means I can have two brother. Okay, so I can say this is my brother and this is also my brother. This is a relation. Okay, but in case of function, we can't say that. Okay, I can say this is also my value and this is my value. I can't have two values. Okay, means let's say if there's a function, you must have, I give you a simple example, y equal to sin x. Okay, this is a simple function. So I cannot say that I'll have at x equal to, let's say, 90 degree. I cannot say this function, I just 90 sine of 90 will be 1. I cannot say minus 1 also. This is not possible, right? In case of function, we have only one image or one value, right? One outcome, or yeah. But in case of relation, we can have multiple images. So this is only one difference, but that makes a relation different from a function. So you need to understand this thing, how a function is different from a relation. Okay. Now I can say f is a function from P to Q, and yeah, its range of f is denoted by R of f as is what, the elements or images of the elements of P, right? So what are they? A and your D and C, E, yeah, right, this is a relation. Now you can also ask C, hello, because here there are two elements who are connected with same. Can it be possible? Of course it is possible. It is possible because two different function can have same value. How it is different, right? Or a function can have same value at 2 points. Let's say I give you yeah, this is a function f of x equal to x square. This is a function, right? From, let's say, real line to real line again. It's a from R to R, a real number to real number. It's a function. Okay. And now if I put the value at 1, it gives 1 square equal to 1, and at minus 1 it is also gives minus 1 whole square equal to 1. So at 2 points, 1 and minus 1 of course are two different points. So but at these two different points the value of this function is same. So we can say image can be same, but image of a function at 2 points could be same, right? But we cannot say at 1 point I'll get two values. That is not possible in case of function. Okay. And yeah, this is what a function is about. Yeah, okay. And we got the range, and let me give me some few seconds to explain you difference between range and codomain. So domain, Q is the codomain. Okay, Q, A, B, C, D, E, F. It's a codomain, right? And it's a range. We can say that range, every element of range are in codomain. So range of F, range of a function is always a subset of codomain. It can be equal to codomain, or but it will either a subset or a same, right? But here we can say it's a subset, proper subset. Proper subset are denoted by this. And if I say there is a chance of like ambiguity and we cannot clearly say whether it is subset or proper subset or same, so we just write this way. Okay, but yeah, here we can see, that's why I'll just remove it. Okay. So this is about range. We have learned about images. These are called images. Okay, this is the image of this element, right, under the function f. And this is not an image, and this is an image. It's an image. It's an image. It's not an image. Okay. So yeah, that's what you take your